The question that I have is, could you do an example on calculating the stresses in a horizontal deposit of soil? Here's the problem that I have chosen to work on here. We have a horizontal deposit of soil consisting of several layers. The water table happens to be at a depth of 1 meter from the ground surface. We are given values for the layer thicknesses and the total unit weight for these layers. The question is to calculate the total and effective normal stresses at point A, which is right here. Here's an exaggerated version of a differential element taken at point A. So the question is to calculate sigma V prime, sigma H and sigma H prime. Because it is a horizontal deposit of soil with no horizontal forces acting anywhere in the soil deposit near point A, there are no shear stresses on this element. Here's a summary slide from one of the earlier videos on Tesagi's effective stress principle, a useful starting point for doing the problem we have at hand here. This is the Tesagi's effective stress principle. Sigma equals sigma P prime plus U. Sigma is the total normal stress, U is the pour water pressure, sigma prime is the effective normal stress. In that video, we considered a container consisting of a homogeneous saturated soil. For this problem, sigma V was gamma set multiplied by Y, where Y is the depth of the point at which we are trying to calculate the stresses at. U is gamma W times Y, and sigma V prime is sigma V minus U. So let's first talk about how we can extend the ideas we just looked at in the earlier slide to a situation where we have a horizontal deposit of soil, like this one. As long as the deposit is horizontal, and all of the layers are horizontal, and there are no horizontal forces acting anywhere near the point of interest, then the mechanics of this problem is identical to the mechanics of a container full of layered soil like shown here. So I've made the layering details to be identical to the details of the layering in the real problem that we are working on right now, so that it'll be easier for us to relate this to this. Say the total densities of these layers starting from the top are gamma 1, gamma 2, gamma 3 and gamma 4. The layer thicknesses of the first three layers are H1, H2 and H3, and this depth right here is little h. The depth of water table to the point of interest is little hw. So let's consider the equilibrium of the free body with boundaries shown by the green lines here. So on this horizontal plane, passing through the point, we have a force F, and that can be split up into the force due to pour water pressure and the force due to what we call the intergranular forces, right, which is the one that goes with the effective stress. And then within the layers, we have the weights acting vertically down, W1, W2, W3, and W4. There are no forces acting on the surface of the soil. Here's the derivation of the equations for calculating these stresses. Referring to this free body diagram, I've summed up the forces in the vertical direction and set it to 0. And we note that F is Fu plus Fi, Fu is U times A, Fi is sigma V prime times A, and F is sigma V multiplied by A, where A is the cross-sectional area of this plane. W1 is the total weight of layer number 1. That will be volume multiplied by the total density. The volume is simply cross-sectional area multiplied by H1. So therefore, W1 is simply H1 times A multiplied by gamma 1, where gamma 1 is the total density, right? The same expression applies to all the other weights. Now you substitute these expressions in our equilibrium equation. We get this equation. Sigma V is simply sum of Hi gamma I. In other words, you sum up the contribution of H times gamma for all of the layers above the point of interest, you get the total vertical stress. So to calculate the pour water pressure at that point, we don't even have to look at the details of the layers. All we need is the total depth of water at that point. And in this case, it's little hw, and therefore U, the pour water pressure at that point, is little hw multiplied by gamma w. Then by Tesagi's effective stress principle, sigma V prime is sigma V minus U. To calculate the effective horizontal stress, we use this equation, right? Sigma H prime equal K naught multiplied by sigma V prime, where K naught is the coefficient of earth pressure. Then the total horizontal stress is simply calculated using this equation, once again using Tesagi's effective stress principle. That's it. So let's go ahead and apply these equations to our problem. So here's the problem, and here are the equations. So we are looking at point A, right? So here are my calculations for sigma V, the total vertical stress at point A. There are 4 layers above point A. Layer 1 has a thickness of 1 meter and the total density of 17 kilonewton per meter cubed. And the layer number 2 has a thickness of 1 meter and the total density of that layer is 19 kilonewton per meter cubed. Layer 3 has a thickness of 2 meters and a total density of 20 kilonewton per meter cubed. And layer number 4 goes only up to point A from the top of that layer. So the thickness to be used there would be 0.8 meters and the density is 22 kilonewton per meter cubed. So what's the unit of the resulting stress here? Well, H is measured in meters, right? And gamma is measured in kilonewton per meter cubed, and this is true for each of the 4 terms we have here. So you can see this simplifies to kilonewton per meter squared. And numbers simplified to 93.6, and the units simplified to kilonewton per meter squared. And if you recall the definition of Pascal, Pascal is Newton per meter squared, right? And therefore what we have here is 93.6 kilopascal. U equals HW multiplied by gamma W, where HW is the water depth to point A, which is 3.8 meters, right? So this is 1 here, 2 here, and then 0.8. At the 3, you get 3.8 meters. And the unit weight of water is given as 9.81 kilonewton per meter cubed. So we get a value of 37.3 kilopascal for pore water pressure, U. Next, using this equation, which comes from Tesagi's effective stress principle, sigma V prime is calculated to be 56.3 kilopascal. Now the relationship between sigma H prime and sigma V prime is this. We are given a value for K naught, 0.4, and we get a value of 22.5 kilopascal for sigma H prime. Finally, adding the pore water pressure to sigma H prime, we get a value of 59.8 kilopascal for sigma H.